All right. Hello, everyone. Anybody here? All right. Yes, there's people here. Great. So hi, welcome back to the course. All right. So on Monday, we were looking at static analysis, right, and specifically the reachability analysis that you are required to do for a Java compiler. It's required by the Java spec, and it's also required for a JUICE compiler. And so this is sort of the main thing that you will be implementing in assignment 4, or maybe already are implementing in assignment 4. All right, and so what did we have here? So the idea was that we were going to define these two arrays in of S and out of S that are indexed by statements. So AST nodes, nodes in the AST that represent statements. So for each statement, you're going to figure out, is it possible for that statement to begin it executing and to finish executing? And the possible answers are maybe or no. And so it's always safe to say maybe, but as I discussed last time, the Java spec tells you have to do this particular analysis that's going to say maybe in the exactly specified cases. All right, and so we looked at if statements, and sort of the general thing that we do for each kind of statement is encode the analysis in these kinds of equations that compute in of the sub-statements of a statement. So in this case, the then clause of the this statement in terms of in and out of the overall statement, and then you compute an out value for the overall statement. All right, so we looked at the case of if statements, and I told you to think about while loops, and that we're going to do while loops next, right? So, all right, so let's do while loops. Right, and then for if statements, I said it's helpful to think of this kind of a flow chart, or to draw a flow chart. So, I mean, we can draw one for a while loop. Right, so let's see. So I'm going to have my while loop, and we'll call it L. And we go into the while loop, and we check a condition, right? And let's say if the condition is false, then we leave the while loop. If the condition is true, then we go into the body, right? And all right, and I'll call the body S. And then the control flow comes together, and we get to the end of the while loop. Right? So there we go. All right. And I can draw some arrows to say the control flow is coming together. And then I can label this with in of L and out of L and in of S and out of S. Okay, and so now I can pretty much make up the equations from this the flow chart. So I've got a while loop, and I'll say while expression, then loop in the statement S here. Okay, and so I need an equation for in of S. And so you kind of just look at the flow chart and you see, like, how do I get to in of S? Well, I go through in of L, and then the expression, okay, I'll say more about the expression, but for now, we're assuming that we don't know whether the expression is true or false, so we just ignore the expression. right? The expression will not itself loop forever, right? Evaluating the expression will eventually terminate with true or false. And so we assume that it terminates and you can get to n of s. So n of s is going to be n of L. So if it's possible to start executing the loop and it's possible for the expression to evaluate to true, then we're going to start executing the body. Okay, now for out of L, right? So I need an equation for out of L. And so, all right, so you know, what would we get? And so it's like in the if statement, we have control flow merging. So we want to take an OR of these two control flow paths. And so, you know, if you come in through this path, then it's n of L. So if the loop is it can start executing and the condition evaluates to false right away, then the loop will finish executing, right? I mean, that's how while loops work. If the condition is false to begin with, then the while loop just doesn't do anything other than evaluating the condition. On the other hand, on this other path, right? So you're going to come through this path if you've gone through the body. And that's not how while loops work, is it? After you, that's not how while loops work at all. All right, that's more like an if statement. All right, so so really, after you've executed the body, you go and evaluate the condition as well. And so the place where things merge is not down here, but actually up here. However, the control flow merge still merges in of L and out of S. So that was sort of the point that I wanted to make, but I was trying to make it with the wrong diagram. So sorry about the diagram, but right. So the point is here you're merging in of L and out of S, and so you want to say that you can exit the loop if either you can enter the loop and the condition evaluates to false, or if you can exit the body of the loop and then you come here and then the condition also evaluates to false, right? So I'm going to say in of L or out of S. Okay, and now that I've fixed the diagram, you should actually have that or out of S for in of S as well. But you know, now I'm going to say that you can actually leave out the or out of S. So I'm going to parenthesize it to say you could leave it out and you could just say it's in of L. And okay, and so why? Well, in order to get to out of S, right? If out of S is going to be reachable, well, you must have gotten to it somehow. So if out of S is maybe, then in of L must be maybe already. And so if you're there's no case where in of L or out of S would give you a different value than only in of L. So that would happen, let's see, if, when would that happen? If in of L was no and out of S was maybe, and that can't happen, right? You're not going to be able to reach the end of the body of the loop if you haven't been able to reach the loop at all in the first place. All right. So the equations that you can implement are just in of S. So the body of the loop is going to be reachable if the loop itself is reachable. So in of S is going to be equal to in of L. And out of L is also just going to be equal to in of L. So that kind of simplifies the equations a little bit. Okay. So those are equations for a while loop. I guess, I left it as an exercise on Monday. Did anybody, think about it, try to figure out the equations? You don't have to tell me whether you did or not, but if you did anybody come up with something like this or something different or anything? All right, and now I have to wait for the YouTube chat to it seems to have a delay. Okay, so or maybe not, right? Maybe you were busy with the assignment, which certainly is fine, right? Okay, so now we have equations for a while loop, but now now you look at the Java spec and it throws an extra wrinkle into all of this. Let's see, what should I want to erase the middle here, just so we're in the middle. So let me do the middle. So if you look at while loops, or really any loops in the Java spec, so I guess as part of an exercise, a real exercise that you're going to get to do for the assignment is to generalize while loops to for loops. But I mean, for loops are not all that different from while loops. But so the Java spec throws a wrinkle. So far we've been assuming that this condition E, that we don't know what it evaluates to, right? That it could be true or false, and we're going to consider both possibilities. But the spec makes a special case for a loop where the condition is true. So if I have a loop where the condition is true, say while true S, okay, then the Java spec says, okay, well, if I see that loop, well, then that's an infinite loop, right? It's going to keep looping forever. And so here, the equations are actually going to be different. The computation of reachability is going to be different. So what are we going to do? So in of S, well, it's still going to be in of L, right? Because you come in of L, and then the condition is always true. So you go to in of S, and so in of S is reachable exactly when or the body can start executing if and only if the overall loop itself can start executing. All right. And what about out of L? Well, out of L, so, can the while loop finish executing? So can an infinite loop finish executing? Well, no. I mean, that's the whole point of an infinite loop. And so the Java spec says that for a loop like this, the analysis should say no for out of L. Okay. And I'll, put sort of a side condition. Oops. No, this doesn't work. I'll put a side condition, no break statement in the loop, the body of the loop, right? Because, I mean, if you had a break statement, then even if the condition is true, the loop wouldn't necessarily be an infinite loop. But in Juice, there's no break statements to begin with, and so you don't have to worry about the breaks in Juice, right? So in Juice, if you say while true, it really is an infinite loop, and so these are going to be the rules for that kind of a loop. Okay, so now what about the condition here, right? So if you literally write while true, then where could I write this? Maybe down here. So if you literally write while true, then that is a condition that really is the constant true. What if you write, while 1 equals 1. So, okay, and so the Java spec is going to say this is also equal true, right? And the compiler can figure this out because 1 does equal 1. So, I'm going to say constant. But, and I could come up with other examples here. So as another example, if you have a variable x, and you say while x equals x, it's going to not figure out that this is true. And for this kind of a while loop, it has to use the general equations, right? So it has to assume that x equals x could be true or false. And sort of the reason is that the Java spec tells you that, yes, 1 equals 1 is simple enough that the compiler is required to be able to figure it out, but x equals x is more complicated, and so the compiler is not expected to figure it out. So you're going to use this rule for the second while loop. And so more specifically, in section 1528, 28, specifies what's considered to be a constant expression and what is not constant. And so the rule for while loops is that if you have a constant expression as the condition, and that constant expression evaluates at compile time to true, then it's an infinite loop, and you have to use these equations for it. Just as a crazy aside, I guess in Java, there's a case where x equals x could actually be false, and that's if you have floating point numbers, and there's a weird floating point number called not a number that is not equal to itself. So in that case, I guess this could actually evaluate to false. But really, the reason is that even if it does, like even if x was of type int, so then it is always true. The spec has to delimit which kinds of expressions are simple enough for the static analysis to evaluate them at compile time, and which ones are too complicated, right? You could think of more and more complicated expressions that are possible to evaluate at compile time, but no actual compiler can figure them out, right? We talked about decidability or more specifically that it's undecidable in general whether a particular expression is going to evaluate to true or false at runtime, and the spec just gives a list of certain specific expressions for which it's easy enough for the compiler to figure it out. Okay, so I think I've talked a lot about that. So the point is, an infinite loop, never ends. All right. So what are some consequences of that? Well, we talked about when it's an error, right? And in terms of reachability of code. So in Java and in Juice, if you write an infinite loop and you put code after the infinite loop, you will get a compiler error here, right? Because the code after the loop will be unreachable. Similarly, for the return, right? If you write an int function and a function that is supposed to return an int, and you forget the return statement at the end of the function, but you put an infinite loop in there, that's okay, and it's not going to require you to put the return statement. All right. So, I mean, partly this is kind of just a fun illustration of some of the things that a static analysis does. It happens to be in the Java spec, and so you get to implement it in the juice assignment. So there's a related set of equations for when the condition is while false. Okay, and so here the condition, the equations are sort of what you would expect. So in this case, for while false, what should n of s be? So if I have a loop where the condition is always false, so it always just falls through, never executes the body, so now n of s is going to be no, right? Because the body will never, ever execute. And so a while false loop will actually always be rejected unless the body is just a semicolon, right? If the body is if there's any actual statements in here, then those statements are unreachable and they cause a compiler error. And then out of L is going to be in of L, I guess like here, but also if I go in the loop, it's false, I go out of the loop. Okay, so I mean, the false case is kind of not really that interesting, but just an extra detail to include in there in the implementation. Now, you might wonder, okay, if I'm not allowed to say while false and some instruction, what about if false and some instruction? So, after all, like here, right, n of s, or the body of the loop is not reachable, so the compiler gives a compile time error. But if you put an instruction in, or if you put a statement inside an if false, then it's also not reachable. And so, shouldn't it also be rejected? But Java says, nope, that's fine. So this idea of evaluating the loop condition to a constant true or false and adjusting the analysis applies only to loops. It does not apply to if statements. And you might say, okay, why? That's weird. Why not do it for if statements? Like we can do it for if statements if we're doing it for loops. And sort of the motivation in Java is one common pattern is if you want to sort of comment out a piece of code and make sure that it doesn't execute at runtime, right, for debugging purposes or whatever. So one common thing that people do is they say if false, and then they put their curly braces around their code. And nobody ever writes while false, even though you could, right? I mean, while false and if false work the same way. But apparently, if you write while false, Java considers it a bug. If you write if false, then it considers it like something that you're doing for debugging, and it allows it. So you can agree or disagree with that motivation, but that's sort of that's what the rules of Java are. And part of implementing a compiler is you implement the spec and you don't ask questions, right? You do what the spec says and leave it to the spec writers to make those kinds of decisions, which sure, I mean, in many cases they are somewhat subjective decisions. Okay, so these are equations for while loops, and we'll have sort of the analogous ones for for loops as well. I'm going to leave those as an exercise. Any questions about these before I go on to the other kinds of statements? I mean, we've covered if statements and while loops. Those are the most interesting ones. The rest of them will be simpler. So any questions here? All right. Okay. So what other kinds of statements are there? Well, I talked about return statements here somewhere. I said we're going to define out of return to be no. So we should do that. So if I have a return statement or a return expression statement, right? So either a return with nothing, like from returning from a void method, or a return that returns an expression. Well, here there's no substatement S to worry about. So we just have to define out of L, and we're going to define out of L to be no. Okay. So I don't know, nothing magic there. I guess the other kind of important statement is a block statement. So a statement can be, oops, that's a curly brace. A statement can be a sequence of statements, right? I'll put a semicolon here too. All right. So, what are the equations for these? And they should be fairly obvious. So I need an in equation for S1, well, for each of the SIs. So in of S1 is going to be in of L, right? So if the block as a whole can start executing, then the first statement of the block can start executing. And then in of S of I is going to be in of S of I minus 1, right? For each, no, not in, out. Right, so if statement S1 can finish executing, then statement S2 can start executing, and so on. Right? All right, and then finally we need out of L. So out of L is just going to be the out of the last statement, S sub n. Okay, so that's for a block statement. Again, any questions, please do ask, but it should be, this is easier than the if statements and the loops that we've done already. All right, and let me squeeze that in here. So L, so here we're going to do sort of the default case. So any other statement, right? So anything that is, not an infinite loop, not a return, it doesn't do anything special in terms of, which other instructions or which other statements will execute. We just say out of L is in of L. Let me just check that. Yep. All right. So for anything else, you don't do anything fancy. It's just if the statement can start executing, then it can finish executing. Now, that hides a little bit of stuff, but so what can this other statement be, right? So one example is an assignment statement, and so it can it just assigns some value to some variable, and so that's not going to get in an infinite loop or something like that. One thing that could happen is that any other statement could be a method call. So you could call some method, right? And this analysis is going to say that if it's possible for you to start calling that method, then it's also possible for that method to return to you. And this is an example of imprecision in the analysis because the method that you call, it could contain an infinite loop inside it, so it might never return to you. So there's a case where in of L could be maybe, but then, and so then out of L is going to be maybe, and you're saying, hey, this method might return to me, but in reality, the method could have an infinite loop in it, and so then it never returns. But, here's where the ability to say maybe is important, right? Because if you had to say yes or no, then you'd have to be able to figure out, does that method halt or not, right? Does that method terminate, or does it run forever? So here we're going to say maybe. However, if in of L is no, so if the method can never even start executing, then of course it's not going to finish executing. Okay, and I've got one more. I guess I said any other statement. So but I have one more, and then we'll be done with the reachability analysis. Okay, so there's one more statement, which is the entire body of a method or constructor. Okay, so when you write a method, right, it has the signature, and then it has the body, and that's a statement that is enclosed in curly braces. But the overall body of the method as a whole, and that's where we're going to say in of L is maybe. And in some ways, this kind of gets the entire analysis started, right? So you say the method maybe can begin executing, and then let's say the body of the method is a block with a whole bunch of statements, one after the other. While the in of the first statement in the method is the in of the block as a whole, which is here is the maybe, right? So if we didn't have that starting point, if we said no, right, then we would be saying that none of the code or that the method itself can't begin executing, and then none of the code in the method could ever execute. Having said that, this is also a form of imprecision, right? Because it's saying that you're assuming that every method in your program could possibly start executing, but that's not true necessarily in all programs, right? You could write a method, and if you never ever call it anywhere, then it's not going to start executing. So, but the analysis, but saying maybe is always safe, and the analysis that that the Java spec specifies says that you should assume that all methods could begin executing, right? Even if they're never called. All right, so now I have the whole system of equations, and you're probably wondering, how do I turn that system of equations into code? So how do I solve these equations? And so in general, it's quite tricky, and I'm going to have more lectures about that. But in this specific case, there's a nice property of the equations that we have for this analysis, which is that there's no cycles. Okay, so in general, in static analyses, you almost always have some equations that recursively depend on themselves, right? So, I suppose with the while loop, you could have if out of L, depends on out of S, and then okay. All right, I'm not going to try to. So as I said, for these particular equations, you don't have any cycles. I'm trying to, tweak the example to have a cycle, and but this particular example doesn't have a cycle. I will give you an example later that will have a cycle, but for these equations, for the reachability analysis, there's no cycles in the equations. So one way that you can implement this is to just write write two functions, right, in of a statement and out of a statement, and really just implement the equations in the bodies of in and out. So recursive functions. Okay, so I'm going to write two functions, one called in, one called out. They each take a statement of the AST, and their implementation is going to look at that statement and find the right equation in all the various equations that I had on the board. And then the implementation is just what the equation says, right? So if you happen to get here, right, if you do in of S and the S is the body of an if statement, then you're going to follow this equation and you're going to make a recursive call on in of that if statement. Okay, and if there were cycles in the equations, then you would get infinite recursion here, and your compiler would never terminate, or it would crash. So this would be bad. So this is why it's nice that this particular analysis doesn't have any cycles. All right, so you could just write these two functions and just implement. The function bodies are going to be just exactly the equations. One sort of slight problem with this is that these functions are going to run in quadratic time if you, in general, right? Because to say evaluate out of, to evaluate one of these, you might need up to order n recursive calls. So if you were to evaluate in and out for all of the statements in your method, you would need order n squared calls, right? Or order n squared evaluations of the equations. So you can memoize to go from n squared to linear time. All right, so you can for the in a real compiler you probably want to do that. For the assignments, n squared is still going to be fast enough, so you don't really have to worry about it unless you want to. And then finally, so this is a general approach that will work for any system of equations as long as they don't have cycles in them. So you could apply it to other static analyses as well. But for this particular analysis, right, because it's so simple, because there are only two cases for each instruction, some groups in the past have found it easier to just not really bother with writing recursive functions and just implement a single pass over the AST that kind of traverses the AST to find all of the statements that are possibly reachable. So I guess, or just an AST traversal. Okay, so I guess the trade-offs are that doing it this way with the explicit in and out sets is sort of closer to the theory, and it's more generalizable to other static analyses. But if it's if you find it easier for the purposes of just getting that assignment 4 done, if you find it easier to just code an AST traversal, do like a depth first search to find AST nodes that are maybe reachable. If you find that easier to just code, that's totally fine for the assignment. Okay, I mean, it's totally fine for any Java compiler, but there's more to it than just implementing a compiler, right? We're trying to learn some general things about static analyses as well. All right, so that's why the more general approach. Let's see. All right, so then we're done with the reachability analysis. So are there any questions, I guess, about any of this, right? How to implement it, or the equations, or the reachability analysis. So while you're thinking of questions, so the next topic is going to be the definite assignment analysis that the Java spec also requires. So let me pause for questions. And I guess while I pause, I will erase stuff. Okay, and as I was erasing it, I just realized the thing about the constant, evaluating constants that JLS, I think it was 1528. That's one of the, not huge, but more interesting parts of assignment 4. So in terms of if you're trying to divide the work between group members, that could be a subtask. Implementing that constant evaluation based on that part of the spec. Okay, so Java definite assignment. Okay, so this is a second analysis that is required by the Java spec. And the point is, to ensure that you never read an uninitialized variable, right? But it applies only to local variables. So ensure that local variables are initialized before use. Okay, and so, as an example, if I'm in some function and I declare X, and, later I return X, or I use X for something else, then, this would be an error. But this analysis would make sure that somewhere in between, right, I have always written a value to X. Okay, and in a straight line example like this, maybe it's sort of obvious, like there has to be an assignment to X somewhere in between. But keep in mind that you could have control structures, right? You could have if statements or while loops or other stuff in between the declaration and the use of X. And so the analysis has to figure out that at runtime, X will definitely have a value before you use it. Okay. So, Java has this interesting analysis, interesting static analysis for this. For the course, I think having you implement one simple static analysis is enough, and I'm not going to make you do 2. So juice, not juice, right? So not juice. All right. So juice is going to do something less precise. And let me do the juice thing over here. So in juice, and I'm going to say that this is less precise, and we'll see what that means in a bit. So in juice, I'm not going to bother implementing a whole other analysis. But in juice, I'm going to make a rule that says, well, hey, if only I just initialized a variable as soon as I introduce it, then I wouldn't have this problem, right? If I initialized x right at the declaration. Local variable always initialized in declaration. Okay, so that's something that's way easier to implement, right? So in juice, you would say I'm not allowed to write int x. I have to write int x, say, equals 42, and then then I'm and I mean you can check that even just as part of parsing, right? You have to check that every declaration has an initializer, and then you've checked it in assignment 1, and you don't have to write a whole other analysis. So this is way easier to implement, but it's less precise, right? So I said less precise, and sort of reviewing what we mean by precision. Well, precision is about programs that are safe, but where the analysis can't figure out that they're safe. So if I get rid of the 42 again, there you go, right? So if I have int x and then I assign x1 and then I return x, that's a program that at runtime is perfectly fine, right? It's not going to read an uninitialized value from x because it's going to initialize it to 1. Right? And the Java analysis can figure out that this program is safe, whereas the juice analysis, it says maybe. It says I can't, maybe it could be safe, but I'm not sure, so I'm going to reject it to be on the safe side. Okay, so juice is going to say, no, you can't write this program without the 42, even though the program is okay, but Java would give you more flexibility. It would allow you to write the program. All right, and there's one other trick that you need for juice. So, the other thing that could go wrong is if I said int x equals x, then, then what happens? So syntactically, this is fine in that x has an initializer, right? It's going to be initialized as soon as you declare it. But its initializer is going to read x itself, and that's bad, right? Because it will read the uninitialized value of x in order to initialize itself. So the other sort of simple rule that Juice adds, is that a local variable cannot appear in own initializer. Okay, so you're not allowed to use the x there, and that that prevents you from accidentally reading x before it was initialized. Okay, and you could phrase this as a form of imprecision as well. You could come up with expressions here where that write to X and read from X within the initializers, so they're actually safe, and yet JUICE won't allow them. But, I mean, those are pretty weird examples. So the point is, these two rules, which are fairly easy to implement, and you do need to implement these two checks in assignment 4 if you haven't partially or completely checked them already in, say, assignment 1. So you do need to implement these checks for JUICE, but they're way easier to implement than building an entire analysis. And they keep JUICE safe, but they're less precise, and so they're less flexible than the analysis that Java implements. Okay, so I'm right. So okay, let me just pause here. I guess first of all, are there questions about the? If there are questions about the JUICE rules, ask away. In the meantime, I'm gonna pause and talk about next week. So next week, I mean, you probably know, but next week on Monday and Tuesday, there's another kind of a reading break. So we're not allowed to have a lecture on Monday. So there will be no lecture on Monday next week, but I will have a lecture on Wednesday next week, right? So the next lecture will be a week from today on Wednesday of next week. Now, as far as assignments go, I know many of you are working on assignment, or most of you are working on assignment 3 this week, right, to finish by Friday. And then there's assignment 4. And so I've covered everything that you need for assignment 4 now. So, you can be working on assignment 4 during those during that break, or after the break. But since I've covered all that stuff, I have a bunch of more material that I think belongs here about static analysis, right? So in particular, I want to show you the Java definite assignment analysis that Java actually implements to more precisely check for initialized variables. And then I want to talk a bit more about the theory of static analysis, right? So that's something that is kind of missing from this course, in the sense of, it's used a lot to justify optimizing compilers, and we're unfortunately not doing optimizations, but it's an interesting topic. But what I want to do is skip ahead to start talking about code generation, because code generation is going to be the big assignment after assignment 4, and I want to give you a chance to get started with code generation. And then after the code generation lectures, I'm going to come back to finish the static analysis lectures. All right. So I want to apologize for that a little bit, because sort of conceptually, I should really do the static analysis stuff now, right? Because this is where it belongs. And I kind of worry, because you're probably still thinking about assignment 3. You haven't even started thinking about assignment 4, maybe. And here I am, starting the code generation stuff. But I do want to get the code generation stuff at least started, and then we'll come back to static analysis. Okay. So I'll come back to static analysis near the end of the course, but let's start looking at at code generation, just so even if you're still not starting with it, right? You're worrying about assignment 3 and 4. You can at least start thinking about code generation, and then when you do get to that point, you can come back and look at the videos and really go into code generation. Okay, so after we've done all the checks, we need to generate code, right? And we're going to generate x86 assembly language. So I have a whole bunch of lectures about how to generate code in general, but I want to first give you a really quick introduction to the assembly language that we're actually generating, right? Because you need to right, you need to know what code you're generating. If you took CS241, you probably generated MIPS assembly language code. So this is going to be, similar but different. All right. Okay, so we're generating x86 assembly language because for the most part, x86 is the most a common kind of processor in at least personal computers these days. So chances are whatever computer you're using has an x86 processor. So we're going to generate code that can actually run on your actual hardware, right? I guess in CS241 we generated MIPS code, and well, I was going to say we don't usually all have a MIPS processor. That's probably not true, because you probably do own a MIPS processor without even knowing it, because it's in many embedded devices, such as internet modems and routers and kitchen appliances. So you probably actually have a MIPS processor somewhere, but not in a form where it's easy to run code on it, right? But here, it's nice to be able to write to generate code that actually runs on your actual machine. So that's kind of the motivation for why x86 specifically, right? So you can actually run the code, and x86 is really not a single assembly language, but more of a family of assembly languages. And sort of the name x86, kind of comes from the history. So the first processor in this family was the 8086, and it came out back in 1978. So most of you were probably not born yet, maybe. And so this was sort of the original x86 processor. So the 86 kind of comes from the name of that processor. And then there were a bunch of other processors, but a significant one was the 8386, and that was in 1986. So much later. And there were other ones in between, but the important thing is that the 386 really changed the assembly language significantly. So so I'm gonna say the original 8086, the assembly language is sort of sometimes just called x86, and this was a language with 16-bit registers, and then the 386. There's different names for the new assembly language that it introduced. So x86 32, or sometimes it's called IA32. And the IA, that stands for Intel Architecture. So Intel was the manufacturer of all these processors back then. And the major change was that 16-bit registers were not enough anymore. And so the machine language and the assembly language were changed to have 32-bit registers, and that kind of required a big, huge redesign, right, of the assembly language. And so the 32-bit version of the assembly language is the one that we're going to use here. Even though it's already kind of old, there's kind of a third major change in 2003. There was the Opteron processor, and so it introduced a new kind of x86 language that's called x86 64. And as you might imagine, this has 64-bit registers, and it was yet another major redesign of the language. Now, despite these years, right, it typically took a long time for these new assembly languages to be adopted, right? So, like, even though it was introduced in 2003, like 10 years later, there were still lots of machines around that didn't support it. So, we're going to do the 32-bit one for various reasons. One reason is that modern computers and modern processors can still run this code. They're all backwards compatible. So you will still be able to run this code on your machine. The other reason is, in Java, ints are 32 bits and not 64 bits. And so since we're implementing Java and Juice, it's going to be a bit easier to implement the 32-bit assembly language rather than the 64-bit assembly language. On the other hand, the original x86 assembly language was a little clunky for a compiler to generate. Anyway, and just have these memories of when I was a kid, right? This was the code that you would write by hand, and here the instruction set was really designed to be written by hand. So for people to write that assembly language, and as time went on, it became more friendly to compilers to generate. So I think if I asked you to compile down to 16-bit x86, it would be kind of painful because it's not really meant for a compiler. But it's possible, of course, but it would be more painful. But the 386 one is mostly reasonable for a compiler to generate, and the 64-bit one is also reasonable. Okay, so we're gonna focus on this one. One other thing that I should mention here, so if you remember CS241 and MIPS, there you had 32 registers. In 1978, that was a huge luxury, and so you only had 8 registers. So there were 16-bit registers. There was only 8 of them, in 1986, they made bigger registers, but you still only got 8 of them. And then in 2003, they thought, well, that's not very many, so we'll give you 16 registers. So just a thing to keep in mind, we're doing the 32-bit assembly language, so there are 8 registers, and we actually won't be able to use all 8. So if you're used to CS241, keep in mind there's going to be fewer registers than you might expect. Okay, so right. So one thing that maybe has you scared, or maybe not, if no one's told you about it, is that the x86 instruction set, it's been around for however many years, right? Lots of years. And it has grown over time. And so people can't even count how many different instructions there are, depending on who you ask. They might tell you, oh, there's like 1,000 instructions or 3,000 instructions. I think there's even, articles on the web that are, looking at the different ways of counting x86 instructions. Okay, and so that's scary, right? Oh dear, do I have to learn 1,000 instructions? No, right? Yes, if you want to be an expert on x86 assembly, it is crazy complicated. But the good news is that the instructions that you really need to generate code, right, that you really need for the compiler are, a handful, maybe 20-ish instructions that were around, back in the original instruction set. And just over time, more and more instructions were added for various special features and various special optimizations. So if you wanted to create, super hyper optimized code that takes full advantage of all the complicated features of modern hardware, then yes, there's a lot of instructions. But for our purposes, there's not too many. And so I'm hoping that this lecture, and I guess the one, a bit of the one next week, is going to be an overview of the most important instructions that you actually need to implement your compiler. Okay, so don't worry about x86 being complicated, because you only need a simple subset of the language, of the assembly language. Okay, so I'm going to start with the registers. All right. So there are 8 of them. And so unlike the MIPS ones that had numbers, in x86 they have names. So EAX, EBX, ECX, EDX, and ABCD, and then ESI and EDI. Okay, so there's 6 of your 8 registers. They have names instead of numbers, and the names, come from this history of this being designed for people to write as opposed to compilers to write. So some of the names had special meanings. So for example, ESI and EDI come from the fact that they were supposed to be used for loop indexes, and the S and the D were for source and destination. Like if you were copying something from one array to another, you were supposed to use ESI and EDI. And there's other connotations with the names that again come from the fact that people used to write the assembly code by hand. From the point of view of your compiler, you can mostly treat these 6 registers interchangeably. And there's just 6 of them, and you could call them 1, 2, 3, 4, 5, 6, but then translate to the names when you generate code. Now I said there's 8, and I've given you 6. So there are 2 more, ESP and EBP. So there's your 8. And in theory, you can use these 2 as 2 more general purpose registers. In practice, ESP is almost always the stack pointer, so the address of the top of your stack in memory. So and like you kind of have to use it as the stack pointer. I guess in theory you don't, but I think you'd be crazy to repurpose it as a general purpose register. Part of the reason is that the instruction set actually has explicit instructions to push and pop things onto the stack, and they assume that the stack pointer is in ESP, right? So if you were taking 241, there you would implement your own implementation of pushing and popping onto the stack, but after you picked a specific register, well, x86 has special push and pop instructions, and they assume that stack pointer ESP is your stack pointer. Okay, and EBP, well, that one is more general purpose, so it is more common to use it as any other register, but sort of a heavy convention is that it's used for the frame pointer, and again, I would recommend that you use it for the frame pointer. It's sort of less important to do that than for the stack pointer, but that is the convention. If you don't remember what a frame pointer is, right, from CS241, I'm going to be going over that when we look at code generation. But for now, I guess the important thing is, these are your 8 registers. You're pretty much stuck with ESP as being your stack pointer, and probably EBP is going to be reserved as a frame pointer, but you have 6 more that you can use, for whatever you need a register for. Okay, so not 31 or not 32, but at least you have 6 registers to use. Oh yeah, I mean, do stop me if there's questions. There's a few more registers that you might see, and if you see them, run away, or if you see them, ignore them. And they are registers whose names end in S, and they're the segment registers. So there's, back in my day, there was CS and DS, and then there was ES, and all these other ones came later. So these you might see in your assembler output or somewhere in documentation, and I would say you ignore these if you see them. Ignore. I can't even spell ignore. Okay, so don't worry about these if you see them. I'll just tell you where they come from. So back in the olden days, our CPU had 16-bit registers. So if you have a 16-bit value, how many different values can it have? Well, there's about 65,000 different values that you can store in 16 bits. And so if you have a memory address in a 16-bit register, you can address 64K bytes of memory, right? 64 kilobytes of memory. And so back in my day, like a lot of the computers you could buy had 64 kilobytes of memory, because that's what you could address with 16-bit addresses. But even in 1978, the x86 said, well, what if people want more memory? And so these segment registers, as they're called, were a hack to enable you to have an entire megabyte of memory, if you can imagine, right? That was a lot back then. And so they were a bit of a hack. But, I mean, as you know, once you introduce a hack, it stays around forever. So here we are in 2021, and these still exist, and they still pop up some of the time. But you shouldn't need to worry about them when you're in 32-bit mode. Even in 32-bit mode, I mean, they are still useful if you need to address more than 4 gigabytes of memory. But, right, because with 32 bits, you've got 4 gigabytes of different addresses. But I mean, who could ever imagine a computer, having 4 gigabytes of memory, right? That's crazy, right? I mean, I remember like saving up my allowance to buy my, second megabyte of memory. But I don't know. This laptop I have here has more than 4 gigabytes. So, and yours probably does too. Anyway, for Juice, 4 gigabytes is plenty, and we just ignore these registers. Okay, so right, registers. So we've got our registers. What about instructions? Well, there's one instruction that does a ton of stuff. So sort of the most common and the most useful instruction, I guess, in x86 is move. And so, spelled move without an E, because that saves a byte in the name. And so you can move between 2 registers. So I can say, move EAX EBX. And, what that will do is it will copy the value of EBX into EAX. So I'm going to write sort of the C pseudocode of each instruction on the right. The semicolon is for a comment in x86 assembly. So you should make your compiler output comments so that you can debug your assembly language code. So here I've just got a comment that says what this instruction does. And while I'm on the topic of commenting, one thing I find helpful is for your compiler, to output comments that tell you the juice code where you came from, right? So, this is a bad comment to output, because everybody knows by looking at the instruction that this is what this instruction does. So don't comment, what the instruction does. But if you put a comment to say, oh, here's the juice code that this instruction came from, then you can figure out where you are sort of in your juice program when you're looking at the assembly code. Okay, and I've got a question. Are we using Intel or AT&T syntax? Right. So x86, I mean, it's a processor, it's a machine language, but in terms of assembly language, there's as you can imagine, over the many years, there were many different assemblers written for x86. And so we're using the Intel syntax, which is the assembly language that Intel sort of introduced back when it introduced the processor. And that's kind of the preferred x86 specific assembly language. There's an AT&T syntax or a Unix syntax, which is which flips the order of all the registers, and it's kind of more general in that there's assemblers for other kinds of processors that also follow a similar syntax. So it's kind of more general, but the Intel syntax is kind of more customized to x86, so it's easier to to read if you're and to write if you're specifically focused on x86 code. All right, so we're using the Intel syntax, and specifically there's a specific assembler that I'm requiring you to use, or at least that I'm making Marmoset use. It's called the NetWide Assembler, or NASM, N-A-S-M, and there's links to it on the course website. But I mean, that's an assembler that requires this Intel syntax, which is what I'm going to show you here. All right. The general idea is that things move from right to left. So if I say move EAX EBX, I'm copying EBX into EAX. So the destination comes first in all of the instructions. Okay, so I can copy things from one register to another, but move can do a lot more than copying between registers. So there's this square bracket syntax, and the square brackets mean that you want to dereference some value. So that means treat the value in EAX as an address and store to the memory location that has that address, right? So you can think of the square brackets as kind of like an array, right? And it's treating the memory as an array, and it's saying, give me the memory location whose address is in EAX. So if I were to, go with a C pseudocode explaining this instruction, the square brackets are like the star operator in C, in that they dereference an address. Okay. Now, in a move instruction, or in a lot of other instructions, you can go crazy and involve lots of registers and possibly constants. So for example, if I have the stack pointer ESP, and I can say ESP plus EBX times 2 minus 5. Okay, so this is a valid x86 instruction, and it does what you might expect, right? It takes the stack pointer, adds 2 times whatever value is in EBX, subtracts 5, treats that whole thing as an address, reads from that address, and stores the result in EAX. Okay, so this is what I mean when I say there's a lot of things you can do with just the move instruction. It's not necessarily a good idea. I mean, often it's very convenient to write something like this. Your compiler doesn't have to generate complicated expressions like these. But again, back in the day when you were mostly writing this code by hand, often you wanted to say something like this, right? I have something on the stack and I want some offset from the stack pointer, and maybe my offset is in EBX or whatever, right? So you can write complicated expressions like this. The exact expressions that are allowed, well, your assembler will tell you whether a particular expression is allowed or not, right? Whether it's too complicated or not. If it is too complicated, then you break it up into various arithmetic instructions. And we'll get to arithmetic instructions in a bit. I know I'm out of time. I just want to finish at least the move instruction. So the other thing that move can do is load a constant. Right? So this is like an immediate constant that's part of the instruction. So this is like, in C, you would say EAX equals, right, gets assigned the constant 42. And finally, like most assemblers, you can use labels. And so labels are names for constants, and usually they are constants that refer to memory addresses. Right? So I could say move EAX, and then I have some name called label. So again, within the assembler, right, the label stands for some constant number, so it could be 42. So the machine language that the assembler will generate would be the same assembly language as here, but the assembler keeps track of the labels for you, right? And you can define a label, I think the same way as in MIPS assembly language. You put the name with a colon after it, and that assigns to that name the address of the next instruction, right? So if you want to name the memory address at which the next instruction will appear in memory, you can do it like this with a colon, and then you can load that address into a register. All right. And one last example of move, which is often you might want to dereference the label. All right, so here the square brackets do the same thing that they did before, but so I'm dereferencing my label. So usually the label is a constant memory address, and by dereferencing the memory address, you're saying read from the memory location that has that address. All right, so later on we'll allocate space for, say, variables in our program or fields of objects or whatever. We'll give them names using labels, and then you'll be able to read from those variables or fields or whatever by taking that constant address that is symbolically represented by the label, dereferencing it, reading the value from that address, and this instruction will read the value into EAX. Right? And you could also store to that address by putting the label on the left of the comma. Okay, I've gone over time. That's the move instruction. I'm going to talk about other instructions, but move, there's a lot of things that you can do with it. That would be multiple different instructions in, say, MIPS or in another instruction set. So I'm going to stop here. So next week, again, no class on Monday, and we will continue x86 assembly on Wednesday. One other thing about next week, the time is changing in Waterloo. So if you happen to be in a different time zone, be aware that the time difference might be changing between Waterloo and your time zone. Okay, so we'll be same time, 1 o'clock on Wednesday, at least Waterloo time. Any questions about anything, I guess, about x86 or time zones or whatever? Any questions? All right. So do 5 seconds and then, okay, so have a good week. It'll be a week before the next lecture. So good luck finishing assignment 3 and assignment 4, and maybe, starting to think about code generation. I will see you next Wednesday. Okay, bye.